All right, let's dive into vectors. We've got some PDFs today on matrices, vectors, lines, and planes, and a university course schedule showing how these ideas are actually taught.
Sounds like fun.
It does, doesn't it? I'm
Okay.
especially curious about how vectors help us solve problems in 3D space. You know, like finding the shortest distance between a point and a line. It sounds almost magical.
Yeah, it is kind of magical how vectors can sometimes simplify complex problems, but before we get to the magic, let's start with the basics. What makes vectors so special is that they have both magnitude and direction.
Okay, most of the time we think of numbers as just like amounts, like the temperature is 72 degrees or there are 12 cookies left.
Exactly. Those are scalar quantities. They only have magnitude, like how much of something there is. But vectors are different. They represent things like velocity or force, where the direction is just as important as the amount.
So like saying a car is traveling at 60 miles per hour, that's just a scalar, right?
Yeah.
But if you say it's traveling 60 miles per hour north, now you've got a vector.
You got it. And we can actually visualize vectors as arrows. The arrow's length represents the magnitude, and the way it points, well, that shows the direction.
Okay, so we can actually add arrows together.
We can. Imagine walking 3 blocks east and then 2 blocks north. Your overall displacement, the straight line from where you started to where you ended up, is the vector sum of those two walks. We can add vectors by placing those arrows tip to tail.
Oh, okay. What about subtraction? Does that work with arrows too?
Yeah, it does. Subtracting vectors is like placing the arrows tail to tail. Then you just draw a new arrow from the tip of the second vector to the tip of the first.
That makes sense. Now, the source material also mentions ake notation for vectors. Is this where things start getting really complicated?
Not necessarily. Ike notation just uses unit vectors, I, j, and k.
Yeah.
These represent directions along the x, y, and z axes.
So it's like giving each direction its own little arrow, and then we just combine them to create any vector we want in 3D space.
Yeah.
Pretty neat. But I'm also seeing some scary-sounding terms in our sources, like dot product and cross product. Should I be worried?
Not at all. They might sound intimidating, but they're just different ways of multiplying vectors. The dot product takes two vectors and gives you a scalar, while the cross product gives you another vector.
Wait, we can get different results depending on how we multiply? What's the point of that?
Well, different types of vector multiplication give us different kinds of information. The dot product, for example, tells us about the angle between two vectors.
So if the vectors are pointing in similar directions, the dot product is bigger. And if they're perpendicular, the dot product is 0.
Exactly. Which also means we can use it to test for perpendicularity.
Now that is useful. What about the cross product? What kind of information does that give us?
The cross product gives us a new vector that's perpendicular to both of the original vectors. It's a bit hard to visualize, but we can use the right-hand rule to figure out its direction.
Ooh, vector magic.
Date.
But what's the practical use of creating this new perpendicular vector?
Well, for one, the cross product helps us calculate areas and volumes. For example, the magnitude of the cross product of two vectors is equal to the area of the parallelogram they form.
Okay, I'm starting to see the power of this cross product thing. And I'm guessing it comes in handy when dealing with lines and planes in 3D space.
You bet. Remember how we said lines have direction? Well, to define a line in 3D, we need a point that lies on the line and a vector pointing in the line's direction.
That's a great analogy.
Yeah.
So how do we go from that to actually finding an equation of a line?
Well, we can express the line's equation in a few different forms: vector form, parametric form, and Cartesian form. They all represent the same line, but just written in different ways. Let's say we have a line passing through the point with coordinates 1, 2, 3, and with the direction vector of 2, 1, 4. The vector equation would be OX equals OA plus T times U.
Hold on. What are OX, OA, and U?
Right, sorry. OA represents the position vector of our point, 1, 2, 3. U is our direction vector, 2, 1, 4. And T is a parameter that can take any real value. And OX is the position vector of any point on the line.
So by changing the value of T, we can like travel along the line.
Yep.
And I'm guessing the parametric form is where we see those X, Y, and Z components come into play.
You got it. The parametric equations would be x equals 1 plus 2t, y equals 2 minus t, and z equals 3 plus 4t. Each equation tells us how the x, y, and z coordinates change as we move along the line.
Okay, that's starting to make sense. What about planes? How do we define those in 3D space?
Planes are a bit trickier because they're two-dimensional surfaces. So to define a plane, we need a point on the plane and two vectors that lie within it.
Two vectors. It's like building a framework for the plane using those vectors.
Exactly. And again, we can express the equation of a plane in various forms, but to find the Cartesian form, we'll need to use the cross product.
A cross product is back, so we take the cross product of those two vectors that define the plane. But then what?
That cross product gives us a normal vector, which is a vector that's perpendicular to the plane. And this normal vector is key to defining the plane's equation in Cartesian form. If the normal vector has components, a, b, c, the equation of the plane looks like this. X plus y plus cz plus d equals 0.
Wow, it's amazing how all these pieces fit together. I'm feeling ready to tackle some of those 3D problems we talked about at the beginning, like
Yeah.
how do we find the intersection of a line and a plane?
That's where things get really interesting. We can substitute the line's parametric equations into the plane's Cartesian equation and solve for the parameter t. That tells us where the line and the plane collide.
So we're basically finding the point where the line pierces the plane. But what if they don't intersect?
That's possible too. The line could lie entirely within the plane, or they might be parallel and never meet. Vectors help us figure out all those possibilities.
Okay, my mind is officially blown. What about finding the distance between a line and a plane? Or between two lines?
Those are great questions, and we'll definitely dive into those, but first, let's take a quick break.
Sounds good. I'm ready to recharge and then get back to this 3D vector adventure. Okay, I'm back and ready for more 3D geometry puzzles. We were just about to get into finding distances between lines and planes.
Right. Let's start with finding the shortest distance between a point and a line. This is where the power of the cross product really shines.
How so? I thought the cross product was mainly for areas and volumes.
Well, it is, but it also helps us find those perpendicular vectors, which is key here. Imagine you have a point in space and a line. We can draw a vector from that point to any point on the line.
Okay, so we have a vector connecting our point to the line. But how does that help us find the shortest distance?
We also have the direction vector of the line, right? Now, if we take the cross product of those two vectors, we get a new vector that's perpendicular to both of them.
Ah, so this new vector is perpendicular to the line and to the vector connecting our point to the line. But how does that give us the distance we're looking for?
Well, that perpendicular vector is essentially bridging the gap between our point and the line. Its length is the shortest distance between the point and the line.
Whoa. So the cross product gives us a vector that not only points in the right direction, but also have a length that represents the distance we want.
It is, and it really highlights how vectors can encode multiple pieces of information simultaneously, Now, finding the distance between two lines can be a bit trickier depending on whether the lines are parallel or not.
Okay, let's start with the simpler case. Parallel lines. How do we approach that?
If the lines are parallel, then their direction vectors are basically the same, or at least scalar multiples of each other. To find the distance, we can just pick any point on one of the lines and use that method we just discussed.
So we're basically reducing the problem to the point-to-line distance case, which we already know how to solve. Clever. But what about lines that aren't parallel? Things are bound to get a bit more complicated there.
They do get a little bit more complicated, yeah, but vectors still come to the rescue. In this case, we need to find 2 points, one on each line, such that the vector connecting them is perpendicular to both lines. The length of that connecting vector will then be the shortest distance between the lines.
Finding those 2 special points sounds tricky. How do we even go about that?
It involves some clever manipulation of the line's equations and, well, a good understanding of vector operations. It might be a bit much to go into right now. But the main takeaway is that vectors still provide a systematic way to solve this problem, even when it seems really complicated.
Okay, I trust you on that. I'm really starting to appreciate how vectors give us this really powerful framework for thinking about and solving those geometric problems in 3D.
Absolutely. And it's not just about geometry. Vectors are incredibly versatile. They pop up in all sorts of unexpected places.
Like where? I'm all ears.
Well, have you ever thought about how vectors are used in data science?
Honestly, no. I tend to think of data science as all about numbers and statistics. How do vectors fit into that picture?
Well, data points often have multiple features or attributes. Think about like describing a house. You might have its square footage, number of bedrooms, price, and so on. We can actually represent each house as a vector, where each component of the vector corresponds to one of those features.
So instead of just thinking about individual numbers, we're thinking about these multidimensional data points as vectors. What's the advantage of doing that?
It allows us to apply all those powerful vector operations that we've been discussing to analyze and manipulate data. We can add vectors to find average house prices or use the dot product to see how strongly those features correlate with each other, and even use more advanced techniques to cluster similar houses together.
That's amazing. So vectors are literally helping us understand patterns and relationships in data.
Exactly. And this vector-based approach is actually at the heart of many machine learning algorithms. They use vectors to represent data points and perform all those complex calculations, identify patterns, make predictions, and even classify data into different categories.
Whoa, so vectors are powering the AI revolution. I never would have guessed that. What other surprising applications are out there?
Well, since you mentioned being fascinated by 3D graphics earlier, have you ever considered how vectors are used in computer graphics?
No, actually, I always imagined computer graphics were all about pixels and code. How do vectors even come into play?
Oh, pixels are definitely involved, but vectors provide the structure and the meaning behind those pixels. Think about a simple line drawing in a computer program, right? That line can be represented by a vector, defining its starting point, direction, and length.
So instead of storing information about every single pixel along the line, we could just define it with one vector.
Exactly. And this makes it easy to manipulate that line. We can move it, resize it, rotate it all by simply changing the values in its vector representation. And this applies to more complex shapes too. Curves, surfaces, even 3D objects can all be represented using combinations of vectors.
So when I'm playing a video game and marveling at those incredibly detailed environments, vectors are working behind the scenes to make it all possible.
They are. Vectors are essential for rendering those virtual worlds, controlling how objects move and interact and creating all those visually impressive effects.
My mind is officially blown. Again, it's incredible how this one concept, the vector, pops up in so many different areas and plays such a crucial role. I feel like we've only just scratched the surface of what vectors can do.
We have. And as you delve deeper into various fields, you'll encounter even more fascinating applications. But there's also another side to this story, the theoretical side. Are you ready to dive into the abstract world of vector spaces?
Abstract? Oh, I'm not sure if my brain can handle that after all these mind-blowing applications.
Don't worry, it's not as intimidating as it sounds. Think of it as taking those familiar vector concepts we've been discussing and generalizing them to a wider set of mathematical objects.
Okay, you've piqued my curiosity. Lead the way.
Let's begin by defining a vector space. It's basically a set of objects that we call vectors, along with two operations: addition and scalar multiplication. And these operations have to obey certain rules, like those commutative and associative properties that we talked about earlier.
Right.
So these vector spaces can be incredibly diverse. We've been focusing on vectors in 2D and 3D space, but we can also have vector spaces of matrices, polynomials, functions. All sorts of mathematical objects can be treated as vectors.
Wait, matrices can be vectors?
Yeah.
And functions, too. That's bending my brain a bit. How can a function be a vector?
It's definitely a shift in perspective, but it's powerful. As long as those objects can be added together and multiplied by scalars in a way that follows the rules of a vector space, we can treat them as vectors. For example, take polynomials, right? Those are expressions with variables raised to different powers, like, x squared plus 2x minus 1.
Okay, I remember those from algebra class. But what makes them vector-like?
We can add polynomials together by simply adding the corresponding coefficients, and we can multiply them by scalars by just multiplying each coefficient by that scalar. Those operations follow the rules of a vector space, so we can treat polynomials as vectors.
So it's like expanding the definition of vector beyond those arrows we've been visualizing. But what's the point of thinking about polynomials as vectors? Does it actually help us do anything?
It absolutely does. It allows us to apply all those familiar vector tools and concepts to analyze polynomials. We can talk about linear independence of polynomials, find bases for polynomial spaces, and even represent linear transformations between polynomials using matrices.
Whoa, so those vector tools we've been using suddenly become superpowered. But you mentioned bases for polynomial spaces. What exactly is a basis in this context?
A basis is like a foundation for a vector space. It's a set of linearly independent vectors that can be combined to create any other vector in that space. Think of it like having a minimal set of building blocks that can generate the entire vector space.
So for those polynomial vectors, a basis would be a set of polynomials that we can combine to create any other polynomial we want.
Exactly. And the number of vectors in a basis actually tells us the dimension of the vector space. For example, the familiar 2D plane has a basis of 2 vectors, while 3D space requires a basis of 3 vectors.
Ah, that's why we call them two-dimensional and three-dimensional spaces. But what are those polynomial vector spaces? What's their dimension?
Well, the vector space of all polynomials of degree 2 or less has a basis of three vectors, 1x and x squared. So it's a three-dimensional vector space, even though those vectors aren't arrows in space.
Wow, that's mind-bending. So even though these abstract vector spaces might seem far removed from the familiar world of arrows, they still have dimensions, and we can still use those familiar vector concepts to understand them.
Exactly. It's a beautiful and powerful area of mathematics, and there's still so much more to explore.
I'm ready for more. What's next on our vector adventure?
Well, we've talked about how vectors can represent data and how they can be generalized to these abstract vector spaces, but there's one more key concept we need to explore: linear transformations. These are special functions that map vectors from one vector space to another.
Mapping vectors between spaces. That sounds intriguing, but my brain is feeling a bit overloaded right now. Maybe we should save those linear transformations for the next part of our deep dive.
You're right, we have covered a lot of ground today. Let's take a break and then come back refreshed and ready to conquer those linear transformations.
Okay, I've had some time to think about all that abstract vector space stuff, and I'm ready to tackle those linear transformations. They sound kind of like teleportation devices for vectors.
Haha, that's one way to think about it. Linear transformations are basically functions that map vectors, from one vector space to another. But they're not just any functions, right? They have to follow very specific rules that preserve the structure of the vector spaces.
Structure. What do you mean by that?
Well, remember those operations we talked about? Addition and scalar multiplication. A linear transformation has to respect those operations.
So it's like saying the transformation has to play nice with the rules of the vector space. It can move vectors around, but it can't fundamentally change how they behave.
Exactly. And these transformations are incredibly important in all sorts of different fields.
Okay, I need a concrete example. How about something from the real world?
Sure. Think about rotating an image on your computer. That rotation is actually a linear transformation.
Okay.
Each point in the image, represented by a vector, gets mapped to a new point. But the relationships between those points, like the distances and the angles, are all preserved.
So it's not just about moving individual vectors around. It's about transforming the entire space in a consistent way, like rotating it or stretching it.
You got it. And this idea of transforming the whole space shows up everywhere. In physics, linear transformations describe rotations, reflections, and even changes in scale. And in computer graphics, they're used to animate objects and create special effects.
Okay, I'm starting to see how powerful this concept is. But how do we actually define and work with these transformations? Do we need some kind of special mathematical machinery?
We do, but it's machinery we've already met: matrices.
Wait, matrices can act like functions that transform vectors.
They can. Each column of a matrix basically tells us where the basis vectors of the original space get mapped to in the new space. And to actually perform the transformation, we just multiply the vector by the matrix.
So all that matrix multiplication stuff we talked about earlier is suddenly relevant.
It is. And matrices are super efficient for calculations. But they're not the only way to represent linear transformations. We can also describe them using equations or even geometrically.
So we have this whole toolbox of techniques for working with them. What kind of interesting properties or theorems do these transformations have?
Oh, there are so many. One important concept is the kernel of a linear transformation. It's the set of all vectors that get mapped to the zero vector.
The zero vector, that's the one with all its components equal to zero, right? So the kernel is like the set of vectors that gets squashed by the transformation.
Yeah, that's a good way to think about it. And the kernel can tell us a lot about the transformation. For example, if the kernel only contains the zero vector itself, then we know that the transformation is one-to-one. That means each vector in the original space gets mapped to a unique vector in the new space.
So it's like a very exclusive club where only the zero vector gets in.
Exactly. Then we have the image of a linear transformation. It's kind of the opposite of the kernel. It's the set of all vectors that can be reached by applying the transformation.
So it's like all the possible outputs of the transformation.
Yeah.
And the dimension of the image is called the rank of the transformation, right?
Exactly. The rank tells us how much of the new space the transformation covers. And there's a nice theorem that connects all these ideas together. It's called the rank nullity theorem.
Ranktality sounds ominous. What does it say?
It states that the dimension of the original vector space is equal to the sum of the rank of the transformation and the dimension of its kernel.
Whoa, so the size of the original space is split between what gets squashed in the kernel and what gets mapped to the image.
Precisely. It's a balancing act. And this theorem has all sorts of implications, from solving systems of equations to analyzing data.
It's amazing how all these concepts are connected. We started with simple arrows, and now we're talking about these really abstract vector spaces and transformations.
It really is. And we've really only scratched the surface. There are so many more amazing ideas out there waiting to be explored.
Well, my brain is definitely full for now. This has been such an incredible deep dive into the world of vectors. I've gone from feeling intimidated by them to, well, actually fascinated by their power and versatility.
It's been a pleasure guiding you through this mathematical landscape.
A huge thank you to our expert guide and to our listeners. Keep those vector arrows pointing forward, and we'll see you on our next deep dive.